Hi everyone, Professor Gassimi here. In this component of the lecture, we'll be discussing recurrent neural networks. Now, the primary weakness of the Markov approaches that we discussed earlier is that they're limited by the context window that we choose. Again, think back to homework 2. If we chose trigram models, they tended to create things that were a little bit more believable, for example, than bigram models. And those tended to create things that were a little bit more believable than unigram models. So the context window mattered, right? And similarly, if we were using a maximum entropy Markov model, the context would matter there too, right? I mean, so let's say I had a word vector for cat. I had some indication of capitalization, and I had what the tag, the part of speech tag, whether it was a noun, a verb, or an adjective for the previous time step and the future time step. And I wanted to predict what the part of speech tag was for a given time step or given word. Well, this context window, if I made it larger, it would probably improve the performance, but I get stuck now with having to choose, how do I choose the context window so that I don't sort of exclude points in my data because maybe not all sentences have context that's large, and you start running into all of these sort of tricky corner cases that you have to deal with. So it would be super lovely if we didn't have to choose a context window at all, but if the model could just kind of retain some history of the information it used when it was making its decisions and just take care of all of that for us. So remember that this is a neural network, and I want to just say from a nomenclature perspective that remember that neural networks have input layers. So for example, this is the word vector for the sequence position 2. This is the output label at sequence position 2 that comes through the activation layer or the final output layer. And then everything in the middle is referred to as a hidden layer. Well, one thing that we can do is we can take the output of our hidden layers or one of our hidden layers, and we can feed the outputs of those hidden layers in at one point in the sequence, let's say x1, as an input in the next part of the sequence, let's say when we're considering information from x2. And we can use that to augment our information for the prediction purposes, right? And this is going to work very well. Why? Because it's recurrent, right? That means that when I'm making predictions about the tag y3, it includes information from what was relevant at y2 and y1. When I'm making predictions for the tag at y5, it will contain information from y4, y3, y2, and y1. Now, practically, the way that this gets sort of laid out as an input, if you were going to code this up, is no different than the way that you create a regular old feed-forward neural network. It's just that you have to keep track of what these activations were from this hidden layer, and then at the previous time step, and include them as new features or inputs to your model in the following time step. So for example, these are the hidden layer activations from the first part in the sequence x1, and we're using them in addition to what is being input here at x2 to finally find the value of the tag y2. Okay, I want to make it very clear that this is really, from a mechanical perspective, all that's happening. And we're still performing the same old standard feed-forward calculations. It's still gradient descent. It still uses backpropagation. There's no extra magic that's happening here. It's just that we're doing these computations sequentially, right? I first compute the value of x1 and get a y1. I then take whatever that value of the activations was, I stick it over here. And then when I'm doing x2, I use x2 plus whatever the activations were from that x1 produced, and I use those together to get the value of y2, and I just keep rinsing and repeating over and over and over again with a for loop. So these sets of activations, if you read, for example, our textbook, these sets of weights that describe the strength of the connections between the hidden layer activations in the previous time step and the current time step in the sequence are referred to sometimes as U. And like all weights, they're optimized gradient descent, backpropagation. There's nothing special. There's nothing extra that happens here for that. W is optimized the exact same way, and V is optimized the exact same way. Okay, so together, these three arrays, they are static. Once you've trained them, they don't change over time. You basically have one version of those weights, W, U, and V, that persist after you've trained it. I'm bringing this up because one of the things that makes recurrent neural networks a little bit confusing to people is a misconception that these matrices are changing over time, but they're not. W, once you've trained it, is always W. U is always U, and V is always V after you've trained the network once. The only thing that are changing over time are this output, the hidden T, and the Y of T, consequently, and your X of T. These are what are changing over time. These matrices find a nice way of encoding what sorts of things you should be paying attention to from the previous time steps, regardless of the time point that you're sitting in. And that's what makes them actually very powerful. Now, there are many applications for recurrent neural networks. For example, you could use them for sequence generation. Now, this figure that you see here is also taken from the course textbook. You can go and read the accompanying text if you'd like. Effectively, the way you do that is you take an input word, you create an embedding, you obviously put that embedding through your recurrent neural network. You can take a softmax to try to get what the next word is, given what the input word is. And then you can take this and sort of daisy chain it and feed it in as the next input to your same RNN. And again, this gets an embedding. You can use this to get the output of a softmax. You can take the most likely word from that softmax, and you can rinse and repeat over and over and over again. And you could use an RNN in this way, the same way that we used our transition probability matrices and priors for the Markov model in homework 2, right? You could basically use this to generate some text. But because of the way an RNN is structured, you don't have to just include, for example, the input word itself. You could include some other kind of information or features here too. You could say that, hey, given this input word and let's say a 1-0 label for happy or sad, I want you to generate some text. And maybe you could get this chatbot of yours to generate depressed text or to generate very positive, bubbly text based on those labels, assuming you have the training data available. Okay, you can also use RNNs for sequence-to-sequence tagging. We sort of discussed this, right? When the previous example, we said we want to generate a label, whether it's a verb, an adjective, or a noun, right? And we were doing that by putting the data through sequentially and generating those. So parts of speech tagging, for instance, is one of the things people do with RNNs. There's named entity recognition, which is what the NER stands for here on the slides. And then you can also use them for cool things like de-identification. You could run this across a piece of text, and let's say you want to remove or mark which of these are the first names of people. You could train, because let's say that you need to de-identify this so that you can release a government document to the public. Well, you might want to find first names like Janet. You might want to find addresses. You could probably train an RNN, a sequence-to-sequence model, to try to mark the probability that this is sensitive information. And it could, for example, put a 1 out here if it is and a 0 if it's not, or a probability that at least gets you somewhere closer there. And obviously also, if you're doing sequence-to-sequence with an RNN, translation is another obvious thing to do, right? So if you want to move Janet to its value in another language, Will to its value in another language, this is something that you could do as well. Now, I should note that when you're doing translation, of course, it's a little trickier, right? Because different languages have different grammatical structures. And so, one-to-one sort of substitutions may not make perfect sense. But assuming, for example, that we were talking about, let's say, all Latin languages, these substitutions may kind of work right off the cuff. Okay, another thing that you can do with RNNs is sequence classification. So this is what we were sort of motivating our discussion with in the first component of the lecture, right? We said, hey, what if we have a movie review and we want to read in all the elements of that, all the the words that made up that movie review, and then we want to at the very end come up with a classification of it. Well, the way that you do that effectively is, you train this sequence-to-sequence model, which is what an RNN is, and you just kind of ignore all the values of y up until you get to the last one. Because this last one, thanks to the way an RNN is constructed, the hidden state is always collecting information from everything that happened previously. So you can sort of just take the output here, and you could, for example, pipe it through some other kinds of neural network structures and get your output that way. Now, RNN layers can be stacked just like any other layer in a deep network. Okay, so we saw this already with feed-forward neural nets. So I just want to say that whatever you can do with a feed-forward layer, you can also do it with an RNN layer. You can create multiple recursions in multiple places. You can create recursions that go across multiple layers. I mean, there's no sort of rules that prohibit you from setting up the structure as you wish. Now, in practice, what people find is that when you increase the number of layers in an RNN-style deep network, you get an increase in performance, but obviously as you add more layers, you increase the number of parameters you have to tune, and it comes at the cost of your training time. Now, a bidirectional RNN, this is something that you might see if you reviewed papers, for example, basically is referring to training two independent RNNs, where the input is processed from left to right in one case. Okay, so imagine this is just the same RNN that we sort of described earlier. Very simply, we have an X1, we pipe it through here, we get an output, we also get a hidden state, and we feed it back to get, or feed it into information that we combine with X2 to get the next hidden state in the output, and so on, and we follow the daisy chain down. Well, when we follow this all the way through, if we want to make a classification about the sequence, once again, we're going to get this final hidden state, and we're going to get an output, right? Well, what they do is they train one model this way. They take this final hidden state here, and they kind of store it for a minute. And then they train another independent RNN, but that just looks at the sequence backward. Okay, so reads it from right to left instead of left to right. And you take the final hidden state from there, and you concatenate them. I mean, literally, so if those hidden states were, for example, let's say consisted of 3 numbers each, so it was a vector of 3 long, then you concatenate the 2 and you get a 6 long vector. That gets fed in to do some additional processing in other parts before you finally put it through a softmax so that you can get the final outcome class. So this is one of the reasons why in earlier components of these lectures, I spent time trying to get you to understand kind of what a sigmoid is and intuitively sort of how it works with linear functions, because everything you're seeing here is just combinations of linear functions and sigmoids or other kinds of very simple mathematical operations. I don't want you to get lost in the graphs. If you understand those foundational components of how a neural network is built, just understand that we're just daisy chaining multiple things together in order to build a lot of these more complex models. Okay, now another model that I think was sort of the king of sequence-to-sequence modeling in the text domain prior to transformers becoming big is something called a long short-term memory network, or LSTM. And these were shown to improve the performance of standard RNNs by effectively allowing the network to learn how to forget. So here was sort of the impetus for this. You and I don't remember everything that we experience, but the way we had set up the recurrent neural network was it sort of infinitely keeps track of things all the way back in time, right? Because the tag that it generates at position 10 in the sequence depends on 9 and 8 and 7 and 6 and 5 and 4 and all the way back in time. And so as you start moving further and further away from the initial point in time, the kind of information that starts getting stored up can, in practice, not end up being as useful. But anyway, the solution to this problem was the LSTM, which basically was trying to help the network learn how to forget information that was not particularly relevant for the task that it needed to solve. And the LSTM does that by using the exact same input element in the sequence. Remember, we called that X. Here's X. And hidden state information, that was H, remember? So it uses those exact same things, except that it adds a context vector. And this context vector is meant to specify what from the past is relevant and what's sort of irrelevant, what shouldn't be looked at when you're trying to make predictions moving forward. Okay. The way that state vector is computed is also recurrently. So we take some initial state vector, let's say we randomize it. That's the way you initialize weights in neural networks. Remember, you choose a random value. So let's say that we have some initial random value of these, and we say, well, the first thing I want to do is create something in my LSTM that helps me forget information. So what I'm going to do is I'm going to take X, and I'm going to multiply it by some set of weights WF. Okay, so that this is again some linear transforms, right? I'm going to add that to a matrix U of F times the hidden information, the hidden state information, H at time t minus 1. I'm going to add these together and put them through a sigmoid so that the output here are some numbers, a list of numbers between 0 and 1. And then when I multiply with a dot product those 0 and 1 values against the state information, what is it effectively going to do? It's going to kind of mask or deactivate certain things within S of t minus 1, right? Because unless that forget gate is all ones, the vector is all ones from this forget gate, f of t, you're only going to lose information from the previous state from what's happening here, okay? And so that was the forget gate. Well, they also have something called an AdGate. And what this AdGate does is it selects new information to add to the current context. So the way it does that is, just as before, it takes the same x at t and the hidden state information, h at t minus 1, and it uses those to create two matrices, G and I. Now notice one of these uses a tanh activation function. We're going to be discussing what this tanh activation function is in the homework a little. Effectively, though, for the purpose of the lecture, just understand that it's sort of like a sigmoid, except that instead of going from 0 to 1, it goes from minus 1 to 1. Okay, so it allows you to have negative values on the output. Okay, so they do this. One of these activations can be basically a value between minus 1 and 1, and then the other one can be a value between 0 and 1, right? Because it's put through a sigmoid here. And it says, okay, what I'm going to try to do is I'm going to try to figure out, this is going to tell me which direction I want to kind of add the information. And this one's going to tell me a scaling factor on that information, right? So because this is negative or positive, it tells me what the direction of the information or context is that I want to care about. And this tells me how much I should care about it. So I combine those two together with a dot product, and I add that with the previous piece of information from back here, right, together so that I get the next state's information, okay, or this contextual state. Now, that contextual state is added, or multiplied, I should say, with what comes out of this output gate. And this output gate is, again, just, taking another set of inputs from x of t and h of t minus 1, with their own matrices that tell you things about how you combine information for the purposes of the output. That gets multiplied by the state to finally generate the next value of h of t. And once you have h of t and that state information, you can obviously repeat this loop for the next iteration on the sequence. Okay, so the idea here basically is that given the appropriate weights for these various gates, and notice that for each of them, F, G, I, O, there were separate weights matrices. There was a different value of W and there was a different value of U for each of these here. And that's because the transform that you want the neural network to learn that relates the input and the hidden state to construct each of these matrices is different, right? It's not like what we were seeing with the RNN before, where U, V, and W was identical across time. Here, it's still identical across time. It's just that for each of these particular functionalities, we're going to have a separate matrix that will hopefully become specialized as we do our training with backpropagation to make this one help us learn how to forget. These two help us learn how to add new information, and this one help us learn how to format our output so that when combined with the state, we do an even better job predicting what's going to happen.